So now we're gonna learn on how to derive the PFR. Remember, this also forms part of continuous flow reactor. It's called the plug flow reactor. So now in this case, again, to derive the design equation for this, we need to start from GMBE, general mode balance equation. So we're gonna have, just like how we did for other reactors, FAO minus FA plus the integral of VR RA dV is equals to dN sub A over dt. Remember why I'm writing sub A's and whatnot. Assume that our reactant is A to give the product whatever. So now at this point in time now, when we do the assumptions, this one's going to be a little bit different for PFR. This is what we're going to look at, okay? We have the inflow, we have the outflow. And then I want us to talk about this. VR, RA, V will be equals to RA multiplied by change in volume. So here we are looking at the concentration, and we are also looking at the, let me do this. Okay. Where was I? I was saying the reason why we're writing this is because we are looking at the concentration, and we are also looking at the rate of reaction that vary with space, okay? So at this point in time, we're just gonna let this integral form of RA dV to be equals to RA change in V, okay? Because of the reason that I gave to you, the concentration and the rate of reaction vary with space, okay? And then now, another thing that we can also look at, it is the NADT. dN sub A dt will be equals to 0. Why? Again, we are looking at the steady state, just like CSTR, steady state. So now what we're going to do here is we're going to incorporate this to the equation. So we're going to have A sub A in this case with V, not plus but minus. Okay. So F sub AV subtract F sub A V plus changing V, okay? Plus what? Plus RA changing V is equals to 0, okay? So now here what we're gonna do is we're gonna divide both sides by changing V. We're gonna transpose this one. Okay, let me just do it. So we're gonna have FAV minus FA, this plus changing V is equals to negative RA changing V. We divide both sides by changing V. I'll tell you why. It's because, again, here we're gonna have to make time. This they have changing volume. We're gonna have to make volume the subject of the formula, just like continuous the tank reactor. So when we divide by V, we're gonna take the limit on this side where we divided by V, and we introduce the integration mathematically, right? So when I divide both sides by V, I'm gonna have something that looks like this: FA bar V minus FA bar V plus changing V is equals to negative RA divided by changing V. So when I take limit this side, as changing V tends to approach 0. Now, this could be into a differential form. By the way, we can write this in differential form, whereby here we have change, right? This minus that before the volume, after changing volume. So we can have dFA divided by dV, which then will be equals to negative RA. So like I said, we're going to have to make V the subject of the formula. So in order for us to do that, we're going to have dV this side is equals to, let me see, we're going to have negative 1 over RA. Okay, let me just write dF over VFA. Let me see, does this make sense? Yes, it does make sense. And then now we can take the integral on both sides. So the integral VR over there, this will be the VR, and then this will be the negative this initial mole into the system and mole that live in the system, molar flow rate. We have dFA divided by RA. Then this will now then be the design equation. Now, again, like I said, RA, talk about the concentration, the conversion factor, and all of those things. You can rewrite this equation when you introduce all of those things, okay? So yeah, this will then be our design equation for PFR.